So here we have another situation in which we know the concentrations of the reactants at the beginning of the reaction. We need to find the concentrations of those and the products as well at equilibrium. We know that the equilibrium constant, KEQ, is 25.0. And knowing the initial concentrations means we need to create an ice chart. We only have three substances this time, H2, I2, and HI. We don't need to deal with the fact that we have two HIs just yet. We will in a couple of minutes. Initially, our H2 concentration is 2.00 moles per liter. I2 is 3.00. And before this reaction has taken place, our concentration of HI is 0. Our change, again, we need to look at mole ratios. 1 H2, 1 I2, and 2 HIs. If we say that the concentration of H2 has decreased by X, mole ratio being 1 to 1 from H2 to I2 would mean that I2 has also decreased by X. And the concentration of HI would not have increased by X because it's 2 HI. It will have increased by 2X. So this is the point where we actually take into account the fact that we had 2 HI. Our equilibrium concentrations, we just combine the initial with the change. Concentration H2 is 2.00 minus X then. Concentration of I2, 3.00 minus X. And concentration of HI would then be 2X. Now we can go and we can take a look at the KEQ equation, products over reactants. So concentration of HI squared. Remember that when we create the KEQ equation, coefficients on compounds become exponents in KEQ. So the fact that we had 2 HI means that our KEQ equation will have HI squared. Reactants are H2 and I2. Filling in what we know, KEQ being 25.0, concentration HI being 2X, but that will be 2X squared. Concentration H2, 2.00 minus X. Concentration I2, 3.00 minus X. Now, unlike the last example, we can't just square the whole right side because our brackets are not identical. It creates a level of complication, just one extra step, one more thing mathematically we'll have to do. So how do we deal with that? Well, we will have to FOIL out the bottom of this fraction. Before we do that, might as well do 2x squared on top, means 2x times 2x, so 4x squared. Foiling out the bottom, 2 times 3 would give us 6. The outsides, 2 times negative x would be minus 2x, but I'm going to combine my like terms right away. Combine that with the negative x times 3 to give us negative 3x. Negative 2x minus 3x would be minus 5x. And the last, negative x times negative x would be plus x squared. put a 1 under the 25 so we can cross multiply. 1 times 4x squared is 4x squared. (25) times the bottom of the fraction. I'm just going to do the math right now. So 25 times 6 is 150. 25 times negative 5 is minus 125x. And 25 times x squared is 25x squared. So the downside in this case is we were not able to eliminate the x squareds. We will need to deal with them. In order to deal with an equation with x squareds, we need to have a 0 on one side. So I'm going to make that on the right side, sorry, on the left side, and move everything to the right. So I'll have to subtract my 4x squared over. I'm also going to rearrange. So subtracting the 4x squared from the 25x squared gives 21x squared. We still have minus 125x plus 150. Ideally, we'd be able to factor this, but the truth be told, that's not often going to happen. Most of the time, we'll need to use the quadratic formula to solve questions like this. In order to do that, we need to identify our a, b, and c. A is the coefficient on x squared, so 21. B, the coefficient on x, negative 125. And c, the constant 150. If you can't remember the quadratic formula, it's easy enough to find on Google. Filling into the quadratic formula, x equals negative b, so negative 125, plus or minus the square root of b squared, negative 125, minus 4ac, all divided by 2a. And I forgot the squared on the negative 125 under the square root. My apologies. Working out the math, negative 125 is just 125. Negative 125 squared is 15,625. And 4 times 21 times 150 would give us minus 12,600. That's all divided by, we'll multiply that out, that's 42. Finish the calculation under the square root. 15,625 minus 12,600 is 3,025. That is still over 42. Take the square root of 3,025, that gives us 55, so we are left with x equals, let's write that a little nicer, 125 plus or minus 55 over 42. My 42 does not want to come out right now. And at this point, we need to split this off into two separate equations. One with our plus, one with our minus. So x equals 125 plus 55 over 42. And x equals 125 minus 55 over 42. Working those out on the left, we get x equals 180 over 42. Divide that out, that would give us 4.3. On the right, we end up with 70 over 42, which works out to 1.7. Now, it may happen that one of these answers needs to be rejected. If either of these were negative, we would automatically reject, because what is x in this situation? X is the change in concentration, how much less or how much more of a substance we get. We can't get negative substance. So, in terms of these questions, positives are the only viable answers. We have 2, so we can't automatically reject on that ground. But if we flip back to the ice chart, and we look at the concentrations of H2 and I2 that we had, concentration of H2 is 2.0, concentration of I2 3.00, we can't change in concentration by more than 2.00 moles per liter. If we change by more than 2 moles per liter, we'd actually use up more H2 than we had. So looking back at the solutions we got, 4.3 doesn't make any sense. We cannot lose 4.3 moles per liter of hydrogen. So that one will get rejected on the basis that it doesn't fit the question. Yes, the math works out. Yes, we get a perfectly decent answer, but in terms of the actual constraints of the question, it does not fit. So now that we know that 1.7 is our only answer here, we can find the equilibrium concentrations of each substance. Concentration of H2 at equilibrium was 2.00 minus x, so 2.00 minus 1.7, or 0.30, if we're going for sig figs, moles per liter. Concentration of I2 at equilibrium was 3.00 minus x, 3.00 minus 1.7, gives 1.3 moles per liter. And concentration of HI at equilibrium is 2x, 2 times 1.7, so 3.4 moles per liter.